Good day, everyone. This is Module 5, Introduction to Artificial Neural Networks. If you remember, in Module 1, we discussed Introduction to Artificial Intelligence. In Module 2, Overview of Fuzzy Logic. Module 3, Fuzzy Logic Controller. Module 4, Machine Learning. And this is Module 5, Introduction to Artificial Neural Networks. From this module, you should be able to understand neural networks from a historical point of view, understand the limitations of primitive neural networks, that it can provide us with new insights on new neural network paradigms. This module will allow you to understand several primitive neural networks such as the McCulloch Pitt's Neuron and Perceptron and how they are used to solve simple classification problems. So what is an artificial neural network? It is an information processing system developed based on the biological brain. It consists of simple processing units called neurons, and all the neurons are assumed to be interconnected. Neurons are activated by certain activation functions. For each interconnection, there is an associated adjustable weight. Signals are processed from input to output by multiplying the weights and activated signals. A learning rule is needed to adapt the weights to solve a particular problem. Training data is needed to train an artificial neural network. So from this statement, we know that an artificial neural network is a machine learning tool because it needs data. And several keywords here that you can take note for now: neurons, interconnection, activation functions, adjustable weights, learning rule. So these are some of the keywords that will be explained as we go along. So this is an example how a biological neuron would look like in our brains and in our nervous systems. Information would flow from this thread-like structure called dendrites to the cell body called soma. It'll be processed, it'll be sent through the axon, and it'll be sent to hundreds of thousands of other neurons. And the connection between one biological neuron to another is called synapse. And as you can see, there's no physical connection, but the information is passed from one neuron to another through chemicals called neurotransmitters. And scientists have emulated this structure and discovered the artificial neuron. So as you can see, there are some similarities. Again, information flows from here. It will be multiplied by weights. So in this case, we have 1, 2, 3, probably more information or data that flows. It will be multiplied by these weights. It will be summed together. It will be passed through a function called the activation function. Then it will be sent to other neurons. So assuming we have n inputs, x1, x2 up to xn, we would have n weights as well, w1, w2 up to wn, and often we have another input whose value is always 1, which will be multiplied by a weight called bias. So 1 multiplied bias, b plus x1 multiplied w1 up to xn multiplied wn, which call the S, the summation of signals, and that value will be passed through an activation function which will determine the output. So for clarity, I have drawn the activation function out of the circle, but often you would just have one circle, and we should know that all the inputs will be multiplied by its weights, and the summation of signals should pass through the activation function in here. And often we would not just have one neuron, we would have a neuron interconnected in a network structure as this. So these are some important names in artificial neural network research. McCulloch and Pitt in 1943, they came up with the first neuron model. Donald Hebb, first learning rule. Marvin Minsky, the first neuron machine. Rosenblatt in 1958 came up with the perceptron. So the first artificial neuron was formulated by McCulloch Pitts in 1943. However, this does not have any learning algorithm, which means the weights are not adapted. So you have to set the rules according to the data, according to the problem, manually. They dealt variable inputs which were multiplied by fixed synaptic weights with the products summed. If the sum exceeded the neuron's threshold, the neuron then fires. If not, it is switched off. So moving forward, in 1958, Frank Rosenblatt from Cornell Aeronautical Laboratory put together a learning machine called the Perceptron that was destined to be the forerunner of the artificial neural networks of the 80s and the 90s. It combined the McCulloch Pitts and Hebbian models, and it did so in a functioning piece of hardware, because those days they did not have a proper or a convenient computer as we do now, so they had to implement artificial neural network in hardware. So this is how the hardware looked like. It's called the Mark I Perceptron. So Rosenblatt machine, which was the perceptron, was complicated and bulky, using motor-driven potentiometers to represent variable synapses. So as you could see in our neuron, we would have weights that has to be set according to our data and our problem. So in the first generation of neural network, which is called the perceptron, they implemented these weights by using resistor value or resistance, which is implemented using potentiometer, and whose value is changed by driving a motor. So Charles Whiteman, holding a sub-rack of 8 motor potentiometer pairs. This is a sub-rack of motor potentiometer rack. Each motor potentiometer pair functioned as a single adaptive weight value. The perceptron learning law was implemented in analog circuits that would control the motor of each potentiometer, the resistance of which functioned to implement one weight. So they came up with a learning rule or learning law to automatically adjust the weights of the neural network. So in order to adjust it automatically, they have to use a potentiometer driven by motors. To a certain extent, the perceptron is shown by Rosenblatt to be able to solve many classification problems. He demonstrated the capabilities of the perceptron and even cut a bunch of arbitrarily selected wires in a densely interconnected multi-node perceptron, and it would still work, though with some degradation. So as you can see, these are the wires, and the neurons are connected randomly. So the connection patterns were typically random, so as to illustrate the ability of the perceptron to learn a desired pattern without the need for precise wiring, in contrast to the precise wiring required in a programmed computer. So you can imagine these are the connection, and this is done by using wires, and they are connected randomly. So, however, it was later discovered that Rosenblatt's perceptron was only able to solve linear problems. So we will see what is a linear problem shortly. In 1969, Minsky and Papert of MIT published an in-depth analysis of the perceptron, demonstrating that the classes of inputs a perceptron could distinguish were very limited. So the perceptron cannot solve complicated problems. Unfortunately, this nails the research in artificial neural networks, and from the 1970s, it became the quiet years in artificial neural network research. So here, image input being adjusted by Charles Whiteman, Mark I Perceptron project engineer. You can see this is the image, and here we have the CDS photoconductors. So a printed character was mounted on the board and illuminated with 4 floodlights. Sorry, these are the floodlights. The image of the character was focused on 20 by 20 array of cadmium sulfide photoconductors, which then provided 400 pixel values for use as inputs to the neural network, which then attempted to classify the figure into one of M classes. So once again, you could clearly see this is a machine learning tool. It's used in this particular example to classify images. So this is a timeline of research in early years. As you can see, 1943, the first artificial neuron, 1958, the perceptron, and after 11 years, right, in 1969, they published the limitations of perceptron. And moving forward, in 1985, Hopfield, a Nobel Prize winner, together with this guy, proposed a number of artificial neural networks based on fixed weights and adaptive activations called the Hopfield network. In 1986, Stanford University developed the backpropagation algorithm, which has been demonstrated successfully for many applications. This algorithm is perhaps the most widely used artificial neural network paradigm and has started a revolution in the field of artificial neural networks. So we will be learning the backpropagation algorithm in the next module. So let's look at this. This is an artificial neuron. So like I said, if you have two inputs, then the inputs are x1, x2, and often, not always, we have additional input whose value is always 1. We will see the why we need this shortly. And the weight of this is bias, and we have weight 1, weight 2. So 3 weights here, bias, weight 1, weight 2, have to be adjusted either manually or through a learning rule or learning law to solve our problem according to our data. So a bias acts exactly like a weight. This is a bias. It is connected as a connection and its activation is always 1, its input is always 1. It is then adapted similarly to the way a weight is adapted according to the learning rule of the artificial neural network. It's used to increase signal levels in the artificial neural network, such as to improve convergence. Some artificial neural networks do not use any bias signals. And the summation of signals that enter an artificial neuron is given by this: x1 multiplied w1 plus x2 multiplied w2 plus the bias, and s has to be passed through an activation function. So we will see some examples of activation functions shortly, and then an output will be produced. So this is an example of an activation function. It's called the binary activation function. So you can imagine the x-axis is the S, summation of signals, and the y-axis is the output of our neuron. So whenever our S, this value, is greater than theta, theta is threshold, whenever it's greater or equal, then our output is 1. Whenever S is less than theta, the output is 0. So a threshold theta is a value that is used to make some form of decisions in artificial neural network such that the artificial neural network will fire or unfire. It is quite similar to a bias, but it is not adapted. So we have to set the value of threshold beforehand. We do not change it. An example of a binary threshold is given as follows. So those weights and biases in an artificial neural network determine the boundary regions that separate artificial neural network outputs. So this is what we are really doing. This is what's happening inside a neuron really. So imagine you have a neuron like this. You have two inputs. And if you are given the task to find what is bias, what is weight 1, what is weight 2, for an AND problem, AND operation, right? So here, instead of, you can see this, the x-axis is input 1, y-axis is input 2, and instead of using the conventional logic levels 0 and 1, we use -1 and 1. So -1 means 0, 1 means 1, right? So whenever x1 is 1, x2 is 1, the output is 1. Whenever x1 is -1, x2 is 1, the output is -1. Whenever x1 is -1, x2 is -1, the output is -1. Whenever x1 is 1, x2 is -1, and target is -1. So the ones in green is our desired output or target. So our job now is to find what is B, W1, W2 such that your artificial neuron can give the correct output, providing it follows or it obeys these equations and using this threshold function. So by selecting correct values of W1, W2 and bias, you are actually forming a straight line that divides your input-output space accordingly. For example, if you set or if you choose W1 to be 1, W2 to be 1, bias to be 0, and threshold to be 1, for example. So you will get a nice straight line that divides your input-output region or space such that your neuron will give the correct output. You can try it in your own time as an exercise. This is called the linear separability. So this is what Perceptron is able to do. So if you have a problem, an XOR problem, for example, if you try to draw the problem of XOR in a similar way, you can see that there's no possible straight line that can divide the space correctly. Therefore, you cannot use perceptron or a neuron like this to solve the problem. So, artificial neural network performance. The performance is described by the figure of Merritt, which expresses the number of recall patterns when input patterns are applied that could be complete, partially complete, or even noisy. 100% performance in recall patterns means that for every trained input stimulus signal, the artificial neural network always produces the desired output pattern. So because artificial neural network is a machine learning tool, so we have to use model evaluation and model validation as we learned in the previous module. So if you are dealing with a classification problem, you can use the accuracy, recall, precision performance measure. If you are using artificial neural network for regression problem where the output is numerical, you can use the root mean squared error as your performance measure. But the difference here is that artificial neural network, the outputs are always numerical. If you compare with decision tree, the output can be class, can be categories, but here the output is always a number because in these neurons we have activation functions and the output or the result from an activation function is always numerical. So you have to decode your training and test output. So if you are trying to classify these three images or these three categories of images, you have to decode this. For example, a cow represents 001, which means when you give the pixel values of this picture to your artificial neural network, the expected output should be 001. Similarly, if you give this picture or the pixel values of this image to your artificial neural network here, the expected output can be 100. Then the next step is to decode. So first you encode, next you decode. So decode means you change back 100 back to mouse. So encoding and decoding. So these are some important artificial neural network parameters. When designing an artificial neural network, one should be concerned with the following. Network topology, how does it look like? This is an example of a topology. Here we have 1, 2, 3 sets of neurons. Each of these is a neuron. We can have, if you have 10 by 10 pixel, then you have 100 input neurons. These are input neurons. These are hidden neurons. These are output neurons. In each neuron, we would have the activation function. And between, so you can see the connection between neurons here. Here you can see that one neuron is connected to every neurons in the following layer. So this is called layers. This is the hidden layer. This is the output layer. Number of layers in the network. This is called the two-layer artificial neural network. Hidden layer, output layer. You can have 3 layers. You can have 4 layers. As many layers as you need. Number of neurons per layer. This is input neurons, so it depends on your data. These are your output neurons. It depends on the target, how you encode your data. And these are hidden neurons. So there's no systematic or proper way to determine how many hidden neurons you should have. So normally we would have more than, so the number of hidden neurons should be more than your input neurons. That's the general practice, but there's no right or wrong here. It's more to trial and error and see how it performs. Choice of activation functions. There are a number of types of activation functions that you can choose from. Network performance, speed to recall a pattern. So of course, if you have huge artificial neural network with many layers and many number of neurons, then when you give an input, it will take fractions of seconds to get the output. So if you are dealing with a real-time application, you have to consider the speed of getting the output from the input. So let's look at some simple neural networks. This is also called primitive neural networks, mainly used as pattern classifiers, usually are single layers in architecture, only consists of one or one neuron or number of neurons in one layer. And it was used in 1940s till 1960s for simple applications such as membership in a single class, either in or out, yes or no, and so on. So McCulloch Pitts is the first artificial neuron which we'll be looking at shortly. Then we have Hebbian or HebNet, the Perceptron, Adeline, and Madeleine. And even though they were simple, they were applied in some real-world applications. For example, detection of heart abnormalities with ECG data as inputs in 1963, where it had 46 input measurements and the output was either normal or abnormal. It was also used for echo cancellation in telephone lines. So these are some real-world examples, and it was proven to work. So let's look at the first neuron of our module, McCulloch-Pitts neuron. It uses only binary activation function, which means the output of your neuron is either, only you have two possibilities, either 0, 1, minus 1, or 1, and so on. And they are connected by directed weighted paths. You have weights that you have to find the values. The connection is excitatory if the weight is positive, and inhibitory if otherwise. So these terms are not used that much anymore. So I will skip this statement because it's quite irrelevant now. So this one, neuron will fire when input to the neuron is greater than the threshold. So we saw the binary activation function earlier. Whenever S is greater or equal than threshold, the output would be 1. Whenever it's less than threshold, the output would be 0 or inhibitory, right? So it takes one time step for a signal to pass over one connection link. No learning, so there's no learning rule here, learning law. You have to set the weights in advance according to your data. So this is a bit troublesome. And of course, those days it was implemented in hardware such as relays, resistors, potentiometers, motors. Maybe not motor, only potentiometer. So this is how it looks like. So once again, the activation function is taken out of the circle for clarity. So in this application, in this example, we can see we have n inputs. Therefore, you should have n weights. You don't have bias. Even if you add bias, it's okay. Depends on the problem that we are solving. So the summation of signals is given by this equation, which is quite obvious. And if S is greater or equal than threshold, the output is 1. If it's less than the threshold, the output is 0. So for example, if you have AND problem, so in an AND function, the output is 1 only when both inputs are 1. So you can see this is our target. You can imagine this is as our both training data and test data. So because this is AND function, you only have 4 possible combinations. Of course, you can include some noise as your data, but because this is for demonstration purposes, you can imagine this is your training data and your test data, which is the same in this example. So whenever x1 is 1, x2 is 0, the output is 0, and so on. And we choose beforehand our threshold to be 2. So your job to find what is W1, what is W2. So by using trial and error approach, you can decide that W1 has to be 1, W2 has to be 1 in order for this to work. So we can test it out now whether the predicted output is equivalent to the desired or target output. So we start with the first data, x1 1, x2 1. So 1 multiply 1 plus 1 multiply 1 equals to 2. So 2 is equal to 2, the threshold, therefore the output is 1. So it's correct. How about this one? The second data. 1 multiply 1 plus 0 multiply 1 equals to 1. 1 is less than 2, so the output is 0. How about the third one? Third data. 0 multiply 1 plus 1 multiply 1 equals to 1. 1 is less than 2, the output is 0. Correct. The last data, 0, 0. 0 multiply 1 plus 0 multiply 1 equals to 0. 0 is less than 2, so the output is 0. So this setup is a correct McCulloch Pitt neuron to fit our AND data. How about OR function? You can try this in your own time, as you will see that you will get the correct output. Perceptrons, I think because this will take a lengthy explanation perhaps with examples, we will continue this in the next part.